Hello, everyone, and thank you very much for attending this webinar of today about technologies for urban biowaste and wastewater valorization. My name is Martin Soriano. I'm HOOP and ValueWaste coordinator working at CETEMA, the Technology Center for Energy and Environment. We are in Southeast Spain, in Cartagena. And this is a joint venture from all these projects that are on screen, you know, SCALIBUR, HOOP, ValueWaste, and WaysTUP. And this is part of this urban circular bioeconomy webinar series that we started like some weeks ago. So this is actually the third webinar that we are organizing after the very successful webinar on selective collection of urban biowaste and the second one on stakeholder engagement and citizen awareness. And these are the next to come that I encourage you to join if you are available. First of all, some basic housekeeping messages. I mean, the main one is for you. You have the option to send questions through our question and answer Zoom module, and also through the chat function on YouTube. I will be having a look to these questions, and after the presentations of our speakers, I will select the best answer for our speakers. And yeah, basically just a brief introduction about this webinar and about HOOP. First of all, about the HOOP solution. So basically, the H2020 HOOP project, our main objective is to support 8 lighthouse cities and regions in developing their large-scale urban circular bioeconomy initiatives. And how is through a project development assistance, a PDA. Basically, our main aim is to remove the technical, economic, financial, legal, etc. barriers to valorize. This is very important. This is the scope of HOOP and also the other projects that we came together today for this webinar, to valorize the organic fraction of municipal solid waste and urban wastewater sludge to obtain safe and sustainable bio-based products. The concept of HOOP, and this is, I guess, where we came together. I mean, SCALIBUR, ValueWaste, and WaysTUP, that were 3 projects that were founded under the same call. So this HOOP can be seen as a continuation of these projects. And basically, these, what we call mother projects, they brought a number of bioprocesses, right? A number of technologies that we are bringing to this HOOP project. So basically, and there is the interaction. So all the knowledge and from this project, from the mother project, from the bioprocesses, we are bringing to this HOOP project through this PDA that I was highlighting before, and this, together with a very strong stakeholder engagement and mobilization approach, is the core of this HOOP project. And of course, we have a very strong replicability strategy. Replication is very important for the European Commission and for HOOP, of course. So we are going to develop, we are going to build, we are in the process of building a network of follower cities, and we are also going to develop a number of tools for making this replication possible. As I was saying before, in these three mother projects of ValueWaste, SCALIBUR, and WaysTUP, we are testing, we are developing pilots for a number of technologies, a total of 15 technologies that we are bringing to whom we are offering to our cities and regions. And here you have the description of the different technologies from the mother projects for the valorization of the organic fraction of municipal solid waste, and also for the valorization of sludge, of urban wastewater sludge. So this is pretty much and in a very brief way what is HOOP about. And now I'm going to focus on today's webinar. So, of course, technology is one of the main challenges covered by our HOOP PDA. So, in particular, providing assistance on technologies to valorize, once again, the organic fraction of municipal solid waste and urban wastewater sludge into added value bioproducts. So, the objective of this webinar is to highlight some of the most promising technologies from our mother projects. And this is our ambitious speaker lineup. So we have very good examples of technologies that we are using in the three mother projects, and we have the opportunity of listening from the developers, from the technology providers, about the current status and main barriers and opportunities from these technologies. So this is everything from my side. So now I'm going to leave the floor to the speakers, to the technology providers. So the first one is Leticia Pereira Gomez from Aqualia, and she's going to present one of the solutions for the urban wastewater sludge valorization from Excalibur. Leticia, good morning, and the floor is yours.
Hello, I'm sharing my screen. So please let me know when everything's ready.
Now it's okay.
Yes. Okay. So good evening, everyone. I'm Leticia Pereira. I'm part of the Innovation and Technology Department of Aqualia, and I'm going to explain the activities that Aqualia is developing within the SCALIBUR project for valorizing sludge from wastewater. So basically, our idea, Aqualia's idea, is to convert wastewater treatment plants into biofactories. Currently, the concept of a wastewater treatment plant is to clean water, so it's not harmful for the environment. But then we have a residue, which is the sewage sludge. And basically, this is our main feedstock with which we're working. Also, we try to implement co-digestion. Co-digestion is not widely implemented in Spain due to legislative barriers. However, we want to work on this. For example, we've tried to co-digest glycerin, which is a byproduct of the production of biofuels, and also to co-digest residues from slaughterhouses, which is a common practice in Spain, or a common industry in Spain. Well, indeed, in Aqualia, we have a different project apart from SCALIBUR, which is Advisor, which is completely working with this type of residues, slaughterhouse residues. So this is the general picture of Aqualia activities within SCALIBUR. So we try to touch in every part of the conventional sludge treatment line of a wastewater treatment plant, and try to optimize it from the sludge pretreatment. So, for example, we've tried different thickening technologies, such as solid gas mixing. We've tried electric fields to try to hydrolyze the sludge before going to the next processes. And we've also tried physical and chemical treatments. Then the core of our activity is to move from conventional mesophilic anaerobic digestion processes, which are the most widely implemented in wastewater treatment plant, and go a step forward and propose new advanced technologies. So we are working in dual or two-phased anaerobic digestion. And then we're also trying to develop a solution for treating sludge in small wastewater treatment plants. So then we have two streams from this anaerobic digestion. We have the biosolids, which can, if we comply with the European legislation, we can use them as solid remediation if they are pathogen-free. And then we have the biogas, which we upgrade to methane using our own technology, which is called ABAD. I'll explain about it later. And it can be used as biofuel for cars. And then we have a side stream, which is CO2 dissolved in water. And this is another core of our research. So this CO2 is converted using a bioelectrochemical system into organic building blocks. So I'm going to talk a little bit more in detail about the three main technologies we have been talking about. So the first one is the dual anaerobic digestion. So basically, this is we are trying to split into two different stages. Conventional mesophilic digestion. So the first stage would be a thermophilic digestion running between 65 and 55 degrees. The aim of this is sanitation. And so here the hydrolyzation, acetogenesis, acidogenesis and acetogenesis is happening in this reactor. So then we have all the methanogenesis happening in the second reactor, which is running at 37 degrees. So the main aim of this is then sludge reduction, because we are optimizing the organic matter reduction. So we will obtain less sludge to manage in the end. The second aim is sanitation. So we comply with the European legislation to spread the biosolids in the land, then optimize bioenergy production, and then reduce the chemical usage consumption, because we have better quality biosolids and less biosolids. So we will use less polyelectrolyte, for example, to the water-aware biosolids. So then the second technology I want to share with you is a decentralized anaerobic digestion. So in Spain, around 30% of the sludge is produced in small wastewater treatment plants, which don't have any type of treatment. So we want to develop a technology which is suitable for this scenario, so without losing a low cost horizon. So for that purpose, we are using this type of bags. These bags are widely implemented in the agricultural sector. But we want to try them in the urban sewage sludge with some improvements such as recirculation. And with this, we want to try to find a in-situ solution for this sludge. So we have to transport less sludge to other places, reducing then the CO2 emissions. The last process I want to talk about, which is the core process, is this transformation of CO2 into added value products. So basically, the biogas goes through a upgrading system, which is basically an absorption column. It's a patented system by Aqualia called a BAT system. So we have a concentrated biogas methane going up from the column, and then we have the liquid stream in the bottom of the column, and this is CO2 dissolved in water. This goes to a bioelectric chemical system, which has a anode and a cathode. So in the cathode, biofilm is growing, and within this system, different electrical and biological reactions are happening, and we produce basically volatile fatty acids, mainly acetate. So the main aim of this technology is CO2. It's a CO2 sink, and we produce added value products from this. This CO2 can come not only from biogas from wastewater treatment plants, but also from solid waste digestion, or it could come from any CO2 source that you can imagine. So this, if this technology is scalable, then it will be a really big success. So rapidly, as I've said, our end products are biosolids and acids and alcohols from the PES. Well, opportunities and barriers that we see. Opportunities basically maximize methane production. And now methane is used as in cogeneration units, and it can be used as a fuel for vehicles. But we see methane as a future potential for a platform for other chemicals, such as H2, that can be used in fuel cells, or ectoine. So optimizing the methane production can be also a success. So then produce biosolids for land application, and this CO2 sinks is also an opportunity. Challenges we see is that with the dual anaerobic digestion we are testing, we are in the limit to achieve the 4th draft European legislation for sludge management, especially for Clostridium. We need to manage the methanogenesis in the first reactor, in the thermophilic reactor. And also we have to consider alternative treatments for biosolids. Anaerobic digestion is an alternative, but we know there are other alternatives that are being studied now, such as pyrolysis, gasification, by other hydrogen production, etc. I'll keep moving. Well, and then finally, just to finish, just say that with all the data we are gathering, we have to produce techno-economical analysis and energy balances just to make sure that the technologies we are offering are in line, are most cost-effective, and energy, and it has a positive energy balance compared with other technologies. So that's the final aim, really. And that's all from my side. Thank you very much.
Thank you very much, Leticia, also for keeping the time. So it was 7.5 minutes. It was great. We already have a couple of questions, but I think that according to the schedule, we are going to hear the next presentation, and then we'll have like 10 minutes, because probably we'll have similar questions to both of you. So after the presentation by Konstantinos, we'll have these 10 minutes of question. Okay. Thank you, Leticia. So the next speaker is Professor Konstantinos Komnitsas from the Technical University of Crete. The floor is yours, Konstantinos.
Well, thank you. Thank you very much, Martin, for the introduction. I will present our Technical University of Crete solution for the urban wastewater sludge valorization in the frame of WaysTUP project for the production of biochar, which can be used as agricultural product, as soil conditioner, as nutrient, and as slow release fertilizer in various agricultural cultivations. The coordinator of our university is my colleague Nikos Nikolaidis, and you see also the research team which is involved in this project. So regarding the biochar production from sewage sludge, we obtain the sewage sludge from the municipal enterprise for water and sewage of Hania in Crete. We also examine the production of biochar from other raw materials, including olive mill wastewater, sawdust from carpenter shops, and we also use compost, which is not pyrolyzed, for the production of biochar. So for the production of biochar, we use the slow pyrolysis, which is a very old method in metallurgy. for the production of metals and the treatment of ores. So we took advantage of the knowledge we had for this industrial process, and we used it for the production of biochar in lower temperatures, varying between 300, 350 to 400, 500 degrees. So in order to produce biochar, we obtain all these feedstocks. We see our young researchers wearing masks, not only because of the COVID, but because of the smell of some raw materials, especially for the olive mill wastewater. So we obtained the sewage sludge and the other raw materials from the area of Chania in western Crete. We purchased a big furnace with a capacity of 750 liters. We placed this furnace in an isobox. We established an off-gas cleaning system, and we plan also to use electricity for photovoltaics, which is this park is next to our unit, in order to reduce the production cost. So actually, we use this feedstock, we apply slow pyrolysis, we try to clean up the off gases, produce biochar, and then apply this biochar in greenhouse and field applications. So the objective is to valorize a waste or several agricultural waste and produce something which can be used instead of fertilizers, but mainly, most importantly, as soil conditioner. Because there are several types of soils with different requirements in nutrients, and this biochar can be used in several cultivations. So we aim to optimize also the process. So you see here, very briefly, the greenhouse, the pots we used, the rates of biochar we used. We applied, let's say, in situ rates varying between 10 tons per hectare and 25 tons per hectare. Of course, we had the control experiments. You see here all the preparations. You see our first greenhouse cultivation with tomatoes. It's like a small jungle in Crete. As you saw, the tomatoes grew very well, and we had a lot of high productivity. You see on the right side of this slide the fertilization we used and the irrigation we used over this first period from the autumn of 2020 to the early spring of 2021. So we analyzed all parts of the tomato plant. You see here the many tomatoes we collected, and believe me, they're very, very tasty. Probably much tastier than those you can buy in the market. So we've done analysis. You see the roots of the plants. The plants grew very well, and we're quite happy. So we've done several analyses of all these parameters. No need to mention them. In order to get a much better idea of the way the test progressed. We see here that the eatable tomatoes and the productivity, we see that with the addition of the biochar, which is the gray columns here, we had the higher number of eatable tomatoes. In the lower graph, with higher productivity. Of course, the differences are not that big, but this is the first trial. So in the field, we expect a much better behavior. In terms of total organic carbon and total nitrogen, we see also that the addition of biochar was quite beneficial. And biochar also improves what is very important is this water stable aggregates in soil. Biochar acts as slow release fertilizer and also enables a much better aeration in the soils. And in terms of optimization, we try to produce biochar with the appropriate acidity in order to be used also in acidic or more soils with higher pH. This is our first field application. What you see here was done last week. So the plants, the tomato plants are very young. We've done several treatments, 6 tomatoes per treatment, and we added biochar in various rates at the top 20 centimeters of the soil. And I hope in a few months we'll be able to give you more interesting results about the productivity and the quality of our field tomatoes. So you see some details here, the way we've done this field tests. And again, you see our greenhouse and the gas collection system. We apply to collect as many as possible of the nutrients present in the off gases and use this solution in our next greenhouse treatment, which is planned for next autumn. Thank you very much. Best regards from Crete. Thank you.
Thank you very much, Konstantinos, and also thank you for keeping the time. So I asked you to stay, and also Leticia to open your camera and be available for the questions. Okay, so we have like 10 minutes of questions. So okay, so I'm going to try to read the questions. Okay, so there is a question, I think it was for Leticia, about the greenhouse gases emissions from sludge. So not only focusing on the treatment, but also on the handling, right, on the transport of the sludge. So what is your approach on this? I mean, are you monitoring the greenhouse emissions derived from the handling of the sewage sludge?
Well, this is we have it in mind, and this is a job we have to do. So obviously we have to compare how much CO2 we are saving from applying all of our technologies. So if we install a anaerobic digestion in a small wastewater treatment plant, we have to do a carbon balance, of course. So we expect that by reducing the amount of sludge that it's going out the wastewater treatment plant, we reduce the carbon emissions. But I'm not sure what if that replies the question. But yeah, we have in mind doing a carbon balance.
Okay, and I think another question for you is about the kind of high advanced approaches for controlling the microbial community inside the anaerobic digester to kind of tailor-made the products that you want to produce, right? So having like because according to the question, like the anaerobic digestion is considered, or traditionally is considered to be like a black box. So it's like the new development is to control this microbial community to produce the products of interest.
Exactly.
So yeah, that's.
Yeah, exactly. We want to have in the first reactor, we want to have the specific microbial community to produce specific compounds, and then another different microbial activity in the second reactor. So that basically helps to achieve optimized biogas production. But what's helping to achieve pathogen removal is the temperature more than the microbial activity. I don't know if that helps respond to the question.
Okay. And probably a last one for you, Leticia. So I'm going to read. So could you please cover the planned value addition to the extracted CO2 from biogas en route to biomethane. I wasn't clear on whether it would just be removed or would be removed and sold as a byproduct.
Okay, probably I wasn't clear in my presentation since I didn't have much time. So what we are doing with the CO2, we separate the CO2 from the biomethane, and this is a liquid current, CO2 plus water. So this is converted into added value product. So we don't sell the CO2 itself, we convert it into other added value products such as acetate or other volatile fatty acids by using bioelectrochemical systems. So we convert it, we don't use it directly. So that's the purpose of the, I mean, that's one of the main processes we are testing now, this bioelectrochemical system to convert CO2 into acetate, which then will be sold to a chemical industries and things like that.
Okay, thank you very much. Some question for Konstantinos. For example, this one, what kind of approach is thought for upscaling of the furnace? So giving an example like fluid bed, rotary drum, etc.
Yes, yeah, that's a question from Miguel. I think we have not studied this, but as an old engineer, I would say that a rotary kiln with a slight inclination like 2-3% seems to be the best furnace. Of course, the use of a furnace and the type of a furnace depends on some let's say characteristics of this. If we're talking about sewage sludge, for example, moisture, so we need to dry it, or if we use olive oil mill waste. But I would say rotary kiln. Rotary kiln is a very good option.
Okay, and then there's a couple of questions from Stuart. Well, the first one, so do you find if there is already a local market for your tasty tomato?
Yes, well, thank you for the question, Stuart. First of all, we do not get too many tomatoes. We got some tens of kilos. And people in Crete, you know, they are characterized by the hospitality as the people in South Italy, South Spain. We share the same water. So for the time being, we shared all these tomatoes among the students, the staff of the university, but everybody was very happy. Crete produced a lot of tomatoes. But in Crete, with so many tourists in the summer, there's always a market for tomatoes and cucumbers and all this green stuff in the summer. Thank you.
And I've got a question, Konstantinos. So, so you are playing with different doses of biochar. So, are you also playing with the, I mean, with the temperature? So, in other words, how did you select the parameters to produce the biochar to be applied to the soil?
Yeah, thank you, Martin. I did not, because of time limitations, I did not show you any results. But depending on the temperature and the quality of the feed material, for example, we can produce biochar with different final pH. Final pH, for example, may vary for the sewage sludge between 5 to 6, while if we use raw material which is olive oil mill waste, the olive oil mill waste is from three-phase mills, not, for example, like two-phase mills like they use in Spain. But we're going to test also two-phase mill waste in our next experiments. So in that case, the pH can be quite high, 9 to 10. So we try to modify the temperature and the way we do the pyrolysis, and get also biochar with specific characteristics. One of them is pH, the other is the content of nutrients. So to be suitable for specific soil types and specific cultivations. I'm not an agriculturist, but we all know that some plants grow in different soils with different pH, and some plants require different nutrients. So what we try to do is let's to model our production of biochar and produce biochar with tailored properties which will be suitable for different soils and different cultivations. Thank you.
Okay, thank you very much for your reply, Konstantinos, and also thank you to Leticia. So unfortunately, we have to move on. There are more questions, so I encourage the interaction with the panelists. You have the credentials, so I think you can continue interaction. But yeah, we need to move on. And thank you very much for the questions, because they were very good, and for the interest. So let's move to this the second block of today's webinar. So far we have presented technologies for the valorization of urban wastewater sludge, and now we are going to focus on biowaste, so on the organic fraction of municipal solid waste. And so the next speaker is Inés del Campo from CENER. Inés,
hello.
Yours. Yeah.
Hello, thank you, Martin. And thank you, James, and the whole project for the invitation to take part in this webinar. I'm going to share my screen. Can you see the presentation?
Yeah, we can see.
Okay, I am going to show you what is within the SCALIBUR project. As Leticia has mentioned before, SCALIBUR is an H2020 project which is focused on the development of scalable technologies for the valorization of urban biowaste. But in this case, I will be focused on the valorization of the organic fraction of municipal solid waste. So here is the content of my presentation. First of all, just a brief introduction of SCALIBUR value chains and where is CENER located in this. In SCALIBUR, we are developing 3 different value chains. The first one, the one in green, is the one about the valorization of urban household biowaste. The second is the valorization of urban sewage sludge, which has mentioned Leticia, and another one is focused on the valorization of HoReCa and retail biowaste. So CENER is focused on the valorization of biowaste for the production of sugars through an enzymatic hydrolysis process for the production of sugars and biopesticides. Also, the sugars will be used for the production of bioplastics by other partners. So what is the hidden potential of the organic fraction of municipal solid waste? From our side, we think that it is very valuable feedstock because due to the high availability, as you know, the amount of biowaste that is produced every day by the people is very high. Here you have some figures, approximately 200 kilograms per European and per year. The generation is very stable and distributed along the territory, and there is an existing and well-developed logistics for the collection. Additionally, we have also the legislation that support that the separate collection has to be mandatory. So and also we will need to reduce the amount of this biowaste that is going to landfill. So it's a very good opportunity to take out the value of this material. We know that it's a very interesting material because it has very valuable components. As you can see in this figure, there is a very high amount of carbohydrates, of proteins, lipids. There is also lignin, depending on the source of the material, and there are also inorganics that can also be valuable. What is the solution that we are developing within SCALIBUR? The idea is to demonstrate the production of fermentable sugars from this biowaste at TRL 6.7 at demonstration scale. We are also going to validate that these sugars can be used in a process, in a fermentation process. So we are going to produce bacterial biopesticides from these sugars, and we are going to perform a techno-economic and environmental sustainability assessment of the whole value chain. This is the approach that we are developing in the project. First of all, we have optimized and validated the process at pilot scale. all the stages from the pretreatment of the biowaste through the enzymatic hydrolysis, the optimization of the doses of enzymes. I have to say that the enzymes have been developed by another partner in the project, by ASA, and we have validated the process at pilot scale, at 200 liters scale. In parallel, we are also optimizing the upstream and downstream processes in order to get a fraction of sugars concentrated and purified to be used in downstream processing. We are upscaling and validating the process at demo scale at a higher TRL level between 6 and 7. In this case, we are using 3 cubic meter reactors for this process. And the idea is to produce a concentrated sugar stream between 400 and 500 grams per liter. And we are also performing the techno-economic and environmental sustainability assessment. We started the demo scale assays in our plant last year at the end of 2020. Here you have some pictures of the assays in the plant, of the reception of the material, the load in the reactors, and the discharge. We are processing approximately 2 tons of biowaste per run, and we completed 1 demo run, and two more are expected by the end of 2021. The expected results of this value chain is the demonstration of an enzymatic hydrolysis process with high solid load in 3 cubic meter reactors. We are planning to produce approximately 500 kilograms of concentrated sugars. We are also applying technologies to reduce the presence of inhibitors, mainly organic acids. And also we are trying to improve the viscosity and pumpability of the hydrolysate and concentrate in order to be used in further fermentation processes. And we are developing an ad hoc separation, purification, and concentration process in order to obtain a valuable concentrated sugar for this fermentation process. Which are the opportunities and barriers? As I said before, we see a very important opportunity in the use of the organic fraction of municipal solid waste, as it is a very high available, low cost, and circular feedstock for the production of bio-based product. We can produce cost competitive sugars that can be used as building blocks for bio-based industry. And we are also contributing to the circular economy because we are trying to reduce waste and stimulating the sustainable growth and contributing to the Europe's green recovery. Regarding the barriers, we have seen that due to the heterogeneity of the bio-waste, the quality depends mainly on the collection systems and the practices in the cities. Of course, the more inners and inhibitors in the feedstock, the more complex and expensive is the conversion processes, because you have to include additional stages in order to reduce the amount of this material. And also another barrier is the public perception of the products derived from the biowaste. Now, just a brief overview of where this approach links with our activities in CENER, in Biomass Department of CENER. This links with what we call the circular urban biorefinery. The Biomass Department of CENER is very focused in taking out the value of different types of wastes in order to get different valuable compounds from them. So we are working with the organic fraction of municipal solid waste, but additionally we are also working with sewage sludge, with lignocellulosic residues and other industrial residues. So the idea is to try to fractionate these materials in order to separate the different components, the sugars, the lipids, the proteins, and to get some valuable components from them in order to obtain different types of products, like biofuels, bioplastic, biopesticides, biosurfactants, and other components. We can work from lab to demo scale, passing through a pilot scale, and the idea is to develop sustainable processes for the production of these valuable components. And here you have some information about our plan for the production of these compounds. We have a plant which is called the Bio2C, the Biorefinery and Bioenergy Center, which is very close to our headquarters. So we have different units, a biochemical, pretreatment and a gasification unit. And it's a very interesting facilities to develop different types of processes and for upscaling processes and support the market uptake of bio-based processes. And that's all from my side. So if you have any question?
Thank you, Inés. I think probably we are going to leave the question for the end. So let's continue with the next speaker, and after the 4 presentation that we have scheduled, we'll have like 15 minutes for questions. So thank you, Inés, and after Inés we have Caterina Coll Lozano from PERSEO Biotechnology. Caterina, when you're available. Thanks.
Thank you, Martin. Could you see my presentation?
Yes.
Yeah, okay. Thank you so much. First of all, I would like to thank the whole project for organizing these webinars and to give us the opportunity to the different companies and the people involved in the project, just to give our vision, our experience and our knowledge in the waste management treatment, giving a new solution just to improve the municipal solid waste treatment management. Okay, then first of all, I would like to introduce our company. We are a SME company that we are focusing in the biotechnological engineering processes. We develop and build up plants just to transform the wastes in valuable bioproducts. We have different infrastructures and capabilities, and we are working in waste valorization to obtain bioproducts more than 15 years. And we have a demo plant of 25 tons per day of capacity, labs in which we can improve the process and design the processes. And here we can see which are our expertise, because as I say, we are working from 2005 in a demonstration plant with a capacity of 25 tons per day, and we are focusing valorisate the organic waste, fraction of waste, and the cellulosic waste through a patented process in bioproducts, bioenergy, and we have specific processes just to obtain bioethanol with different qualities, just to be used as a fuel mixed with gasoline, and and as a chemical building block to produce other bioproducts. And this is our role in the WaysTUP project. Okay, how we work, which is our approach, and that is the same approach that we use in WaysTUP process. First of all, we do a laboratory optimization of the process at lab scale. When we have our objectives and good yields of this bioproduct, we scale up this process in our demonstration plant, and we do a continuous work just to obtain a viable and profitable process, just to pull this process to the market, because we are working always in demo processes. Just ready to be installed in the market. For example, our PERSEO bioethanol process that now it's in the commercialization stage, and the idea is just to always arrive to the final to the market and to the final client of the process. Well, the main objective of the WaysTUP project is just to create new value chains for bio-waste utilization, the bio-waste that we produce in our municipalities. And the project have a multi-stakeholder approach in line with the municipal with the circular bioeconomy. In WaysTUP project, we have 7 different pilots in which we treat different kind of wastes, as municipal solid waste, coffee waste, food and feed waste, and in our case, in the pilot 6, we are focused in the cellulosic rejection wastes. That of course can be mixed with the municipal solid organic waste. The aim of the pilot 6 in the WaysTUP project is to adapt our patented PERSEO biotechnology that is focusing the valorization of organic fraction of municipal solid waste to produce a second generation bioethanol that in the same project is used to produce ethyl lactate via reactive distillation. That is a solvent that can be used in the pharma and food markets. In the project, we tested different cellulosic wastes that are produced in our cities. That is the wastewater treatment plants wipes, the paper and cardboard that can't be recycled in the municipal solid waste treatment plants, and the sanitary textiles as dippers, just to obtain these bioproducts. In the first stage, we improve the processes just to obtain the good yields of bioethanol for these 3 different wastes. And after this, we adapt our PERSEO bioethanol plant just to be able to treat these cellulosic wastes. And after this, the bioethanol that we produce with quality as a chemical building block is used to produce ethyl lactate. At this moment in the project, we finished the optimization at lab scale. We test different conditions just for each raw material. We finished the process. We work in the process, new process design, and in the adaptation of the process in our PERSEO biorefinery. And at this moment, we are starting the demo activities in a big scale. In our plant, we have fermenters from 10 cubic meters until 15 cubic meters. The idea is just to scale up, and we scale up the process in real conditions, in real engineering conditions. We always work with equipment of industrial size, just to be sure that when we scale up, we are going to detect and improve the problems that we are going to have when we go to a real industrial environment, and then we decrease the technological risk just in scaling up the processes. Because, as I said before, our aim is just to arrive to scale up this technology to the final client. And that's all from my side. Thank you for your attention. And if you have any question, as Martin said, I will be available at the end of this.
Okay, Caterina, thank you very much for the very interesting presentation.
Mm-hmm.
So now it's time for Juan Cortés from Entomo Agroindustrial. Juan,
yeah.
the floor is yours.
Thank you. Did you see my screen? I guess so. Yeah.
Yes.
A full screen, right?
Yes.
Okay. Yes. I'm Juan, the R&D director of Entomo Agroindustrial. I will present today our company with this name of Entomo Agroindustrial, the Green Industrial Revolution, because we really believe it is where we are going. Those are the points that I'm going to be talking to you very slightly today. Let's go. Just talking about our mission, we are a service company who commercialize industrial production models to farm insects, or saying in other words, we design for other companies to be exploiting this kind of technology. So our customers are normally either waste managers who are looking for a new manner to be treating the waste in a more efficient way, or companies, normally coming from the food industry, which produce a lot of byproducts every single day. And they are looking for the way to get more profit from this byproduct, or at least decrease the cost of waste management, especially now, because the organic fraction is going to get more expensive in the coming years just for regulations. So by providing services to other companies, certainly we are not limited to one territory or to one specific source of waste, or even to a specific type of facility, because what we do is we adapt the operation to the needs of our clients. And let's say our model is quite open, we can operate globally, not only in one territory. So as solution, we use black soldier fly. Why did we choose one fly to do our process? And well, the logic comes like that. If you want to eliminate waste, and we have to choose those organisms that love the waste, so they will do their endeavor with passion, and flies love garbage, and it is one reality. Once select one species, which is a Metellus, also known as black soldier fly. There are several reasons why. First, their production can be industrialized. It is quite important. You have to think that we are talking about one industry, have to be simple. One advantage we have is we simplify all the all kind of fermenters have several constraints. In the case of black soldier fly, we don't have those constraints. We can be working with different pH, different nutrients, and still we will harvest always larvae with the same composition or similar composition. Second, their product, they are not a pest. They don't like to beat people, neither fly around humans. And it is quite good, because to be producing something which could be detrimental for the environment of the people is not so smart. Also, there is another reason, is according to EU regulation 893 from 2017, this species, the black soldier fly, can be used for proteins for another animals, more specifically in agriculture and pet food. But probably in the coming future, I mean, everything is opening for be using the proteins also in chicken and pigs in not so long time. So what are the challenges? Our process address two challenges which we human beings have. On one hand, we have a large amount of waste that we produce every single day, just food disposals, spoilage of food, manure, digestate, sewage sludge, and so on. Those things have to be managed. And on the other hand, we have another challenge, which is the raw materials. We need a lot of raw materials to produce the goods that we like to have in our everyday. And most of those raw materials have been produced at the other end of the globe, and they are transported to Europe. I'm not against globalization, but it's a really long journey for one commodity. And the most reasonable thing is to produce raw materials locally, and then be used in our industries locally. And it is circular economy, it's the base of circular economy. Our solution, as I said, is the use of black soldier fly. The use of black soldier fly to treat the waste. The good part is, and one side we are treating the waste, but on the other hand we are just producing raw materials which are very demanded for the industry, as proteins, as fats, chitosan, and obviously also fertilizers that can be used in agriculture. And it is quite interesting. The process we use is quite simple. We just copy the nature. We industrialize the nature. So what we do is we industrialize the breeding. We let the adults to make what they should do as adults. They make love the whole day and then produce eggs. We endure this small, we let them hatch, produce a small larvae, endure them. And then when they have size enough, we start to feed them with waste. And when they are totally big in the development, we can harvest and process and obtain the different products. As I said before, this process is quite simple. It's not like one fermenter that can be run if the parameters move from one side to another. In the case of insects, they're quite open. They readjust themselves. And I have to say that there are like two models here. One model is when the larvae are fed with byproducts like vegetables, greens, I don't know, breads, things which are left behind in our human activity. Those larvae can be used to be feeding to feed farms animal. But if the larvae have been fed with waste, manure, sewage sludge, or digestate, then those larvae, they have to go to other processes as industrial products, like for instance, chitosan as flocculant, for instance. And in the template, I have to talk about the ValueWaste. I don't have time. Also, my colleagues, I think, will talk. I'm not going to enter. Partners, I don't going to enter. Although I want to say here, it has been a very nice journey to be sharing with those partners our activities, and we still have some time to be working together. I guess I will learn a lot from them. Let's go more into details about our pilot plant. We are located in southeast Spain, in Murcia region, which is a very good place for the weather is very good. Not only because we have good temperature in summer, but also because we have cold temperature in winter. The pilot plant is to test waste and to obtain metrics. Mainly we do the work for those companies who wants to do their own insect production. They want to have their own insect farm, either for waste treatment or for proteins. And you have to think about something. And when we are talking about one industry, we are talking about being processing or treating like 100 tons, 200 tons of waste a day. And if you want to make a facility able to do that, you regard a lot of calculation and a lot of planning and design. And especially for this kind of investment, you have to estimate very well the CapEx and OpEx. And those CapEx and OpEx will largely depend on the study of the substrate and how is the behavior of the larvae eating the substrate. So how much space do you need to treat your waste? How much energy is needed for venting, for cooling, for heating up? Also, the need of mechanization. What is the mass flow? All this data we can estimate here in our pilot plan and just provide the calculation to other. And you have to think in another industry, you have some base knowledge that you can be applying to do your facility. In the case of this new emerging industry as insects farms, there are not the base knowledge about that thing, and it has to be created new. So it is somehow in our place, in our pilot plan, we have this structure for the companies to be using this knowledge. Obviously, we are in the new generation with digitalization, and we don't want to stop just in the biological part of the larvae or the production. We also want to digitalize. So we are in the process of digitalizing all the process from the things that enter to go out. And if you have an insect farm contracted by us, you will have just to get your cell phone and see how many larvae are entering your system today and how many kilograms of proteins are you getting in the short. Just to talk a little bit more about the ValueWaste project and our contribution, we also create the demo plant, a container which is located in Cañada Hermosa. We reconstruct a disposed container to be more circular, which is the logical part. And this container is mainly to demonstrate the process with urban biowaste and digestate. What I can tell you right now is we know the larvae, they don't like the digestate, but they love the biowaste. The reason why they don't like the digestate are, we already identify what are the reasons. I don't have the time to explain you here, but we can make some readjustment to allow them to start eating the digestate, which is a big thing. For the proportion, we need about 6 kilograms of waste to produce 1 kilogram of larvae. It is very good ratio of conversion. Normally the waste is reduced like 85%. I'm talking more than 85% if we are talking about digestate plus raw urban biowaste. Right now in our pilot, we are like about 60% of our capacity, and we expect to get 100% of our KPI indicators very soon, which is this container should be able to be treating 1 ton of waste a day and to produce about 160 or 170 kilograms of larvae every single day. What we are going to do in the coming year is to collect metrics of this process, and also we are going to get samples of the waste and also the larvae produced with this specific waste. And then we will try to prove right that larvae who have been feeding on waste are healthy or good enough for being used as protein, either for humans or for animals. Right now we are in, or we start the process in TRL6, and we expect to reach TRL8 or 9 by the end of the project. I think we are quite advanced on that thing. We expect to continue advanced. Here you have a scheme of how is the ValueWaste project. We are just here in the digestate part. We get the digestate from the people and just transfer. Martin, you want to tell me to quit, right? Thank you. I'm not going to say anything else.
I didn't say anything. Just appear on the camera. No, thank you very much, Juan. Has been a great presentation. Actually, we have a lot of questions. So, but I'm afraid that we are not going to have time to answer all the questions. So probably I encourage the speakers already, if you have access to the question and answers, to start if you can to answer the question, and then because we still have two presentations from Dimitris and Michael Jensen, two very interesting presentations, and hopefully we'll have some time for some general question at the end of the two lasting presentations. So it's my pleasure to introduce Dimitris Malamis from the National Technical University of Athens. So Dimitris, the floor is yours. Mike, yeah, you should turn the mic on, Dimitris. No, so if you want, we can move to Michael Jensen while you fix probably the sound issue, if Michael is available.
I'm here.
Okay, so Dimitris, we'll come back to you. Okay. Okay, Michael. So it's also my pleasure to introduce you to Michael Jensen from Unibio. Michael.
Thank you.
We can see your presentation, but not yet. Now, yeah.
All right, I'll go ahead. Well, thank you for having this opportunity here to give a very short overview.
Excuse me, Michael. We still cannot see the full screen mode. So it's like we see like one main screen and then one smaller one.
Okay.
It's okay. I mean, we can see it.
It's okay now?
Still not. It's like the next slide is ready on a smaller, but yeah, it's a question of yeah. Now it's okay. Yeah.
It's clear now, right? All right. Let's hear this.
Go ahead.
Yeah. All right. I think my project colleague went through this, so I won't spend time on this. I'll just go to really the index and I'll try to give you a short overview about the role we are playing in the ValueWaste project. Unibio as such, you know, is represented today by me, and I'm Michael Jensen, and I'm the Chief Commercial Officer of Unibio. The vision of Unibio is simply that we have found a way to decouple protein production from farming and fishing, and the technology we apply for that is fermentation simply. And just to make it short, we are becoming more and more people on this planet, and new ways of producing food, feed, and proteins has to be found because we'll be more and more people on this planet here. So that's really why our mission statement, as you see, and our purpose is simply to meet the food security needs of all the people we have on this planet. This is what is really driving us as we speak. I only have 7.5 minutes, so this will be quick. Just to make it short, I think our production and our products are bioeconomical, biocircular, very sustainable, and have, as you could say, a very green environmental profile. And I won't have time to dig into the details, but here you can see some of the effects we have, especially on the carbon footprint, as you see here, where we're really at the very, very low end. And I just want to highlight that as a fact, and then move on. What we are doing here is, the bio-waste we have in this product here is turned into biogas. And when you are making fermentation and producing proteins, you need 3 atomic constituents. You need oxygen, you need carbon, and you need nitrogen. And the biogas, which is what is being the raw material of the value waste here, is our carbon source. So when we do the fermentation, because biogas is a gas, oxygen is a gas, and ammonia is a gas, we just can't apply a normal fermenter. So we have to apply a U-loop fermenter instead. And what we do is we produce the biomass here, and then we take it through downstream processing, where we apply centrifuge, membrane filtration, temperature treatment sections, and spray dryers as such. And I'll have time to just dig a little bit into the details in a moment. Just to make it very clear, we are not just, a lab scale company or demonstration plant company. We have actually already plants available at industrial scale. And I just want to show you that this is actually the first modular industrial plant we have just put into operation in Russia. And just to give you some figures here, the height of these fermenters here are 35 meters tall, and perhaps you can see there are 4 fermenters here. Each fermenter here, as you can see, has a whole lot volume of 50,000 liters each. And this plant here will be able to produce 6,250 to 6,350 tons a year of biomass product that is dried. So this is the sort of scale of economics we're talking about, which we're able to apply as we speak of today. Just to make it clear, the biomass we are producing, where we apply the biogas from the food waste and waste from restaurants, etc., has an amino acid composition that is very, very similar to what you find, for instance, in fish meal. And I think the important thing is that the presence of the 8 essential amino acids is as it should be, and we have more or less the same distribution of these amino acids as what you find in fish meal and what you find, for instance, in soy protein concentrate as well. So the challenge is, when you have single cell bacteria you apply as your biomass, that the content of nucleic acids that is mainly RNA and DNA is not typically only 2 to 3%, but is in the range of 7 to 9%. And this is where you have the challenge as we speak right now. But the standard biomass product, as you see, we have a picture of it here, is light brown, simply because of the fermentation process applied as such. Let's try to dig a little bit into it. The food strategy we have and what are the forecasts out there as we see, you can see that the forecast here will be growing dramatically. And where we are coming from, and probably where my former speaker as well is coming from, is, whether we have to apply the protein and the biomass products we create either as a feed product, as a food product, or perhaps even as an ingredient to cultured meat products as such, we can say, if we don't really look at the economics, if we just look at the biomass as such, we don't really care, because there'll be a demand for everything there. So the thing is that you simply have the biomass available to feed these areas here. So this is the development we see here, that we'll have an enormous growth coming in the years to come, because the number of people on this planet here will be growing. So this is how we see it. If we try to look at a little bit, in just a few, ballpark figures, we estimate right now that the total protein demand for the feed application area and the food application area is in the range of 400 million tons. And if we just look at 1% of that, we actually just talking about a potential that we would like to attack that will come down to roughly about 4 million tons. And bear in mind, you know, that the first industrial modular plant we installed will only be able to produce about 6,000 tons. So my point is here, you know, the market potential out here for these new ingredient products that is coming, both from the black solid fry you heard about before from my colleague, and the technologies we're representing here, the bacteria protein concentrate powder, you know, will be enormous. So the challenge for us is simply not to should we say create a demand and sell the product. The challenge for us is to be able to build in terms of creating capex and opex costs, you know, at a sufficient high speed to really cover the demand we have in front of us. This is the challenge we have. The challenge is not to sell the products. So if we look at what is it actually we have done with this biomass, you know, this is just a fermenter you see here, where you simply make sure to save the biomass available. But what we have actually accomplished here is, you know, instead of just looking at the biomass, we have actually managed, you know, to fractionate and isolate some of the should I say, the building blocks of this biomass here. And I've just decided to present two building blocks today. One is the area where we're actually playing around with reducing the nucleic acid content here from 7 to 8 down to 2 to 3%. And the fraction you will create here will then be a biomass where you have a reduced content of nucleic acid. You will have a stream where you have bacteria protein concentrate or bacteria protein isolate. That means you will have concentration of proteins in the dry matter here in the range of 35 the whole way up to 90%. You will have a nucleic acid fraction, and you will have a mineral fraction as such. So this is one way of going. If you decide to simply split the biomass into individual constituents, you will have another fraction where you can play around with the cell walls and the fatty acids. You will have the same protein concentrate and isolate components, the same nucleic acid contents, and find the minerals content you see here. So I'm just illustrated, if you have a biomass content of 1,000 tons, what are the amount of constituents you will find if you go for these two routes as we speak of today. So this is what we have accomplished to create as we speak as of today. So I think my time is just coming. I think Juan went through this already, and Martin will cover it up. So I just would like to avoid repeating myself for what Juan did, and just say thank you for your attention and give the word back to Martin. Thank you.
Thank you very much, Michael. And then we're going to finish with this set of speakers with Dimitris Malamis from the National Technical University.
Hi, Martin, can you hear me now?
Yeah.
Okay. I had to leave the webinar and just enter again.
Yeah.
Okay. Now I'm just sharing my screen. Just give me a second. Can you see the presentation?
That's okay. Yeah.
Yes. Okay.
Yes.
Hello, everyone. My name is Dimitris Malamis. I'm going to give you a presentation on behalf of NTUA, on NTUA team. Professor Maria Loizodi is the coordinator of NTUA to the WaysTUP project, and research team also composed of Barabuti Eli and Mai Sofia. So in our case, we're developing a pilot plan aiming to convert organic fraction of municipal solid waste to bioethanol within the framework of WaysTUP project. So the pilot plant is installed in NTUA premises in Athens, Greece. We use source-separated biowaste as feedstock, including food waste and green waste. Sustainable City is a project partner which is responsible for providing us the feedstock, and NTUA is responsible for the operation of the unit. As I said, the plan aims to bioconvert source-separated biowaste to biosolvents and mainly bioethanol via saccharification and fermentation process. So we did the systematic sampling and characterization of the collected feedstock for the municipality of Vari Voula Vliagmeni, located in Attica region in Greece. Up to now, we've performed 5 waste analysis campaigns, and as we see from the results here, we conclude that the composition of the collected biowaste doesn't have, let's say, has a low fluctuation, and the total hydrocarbon content is sufficient. It's over 45% in order to produce bioethanol. And concluding that is that the fact that we do have a high potential for bioethanol production. Now about the prototype system, it includes initially a commercial food waste dryer, aiming to dehydrate the collected feedstock. Then we have a 2 interconnected bioreactor system, where the main bioconversion process takes place by enzymatic hydrolysis and providing the customized enzymes, and then fermentation by providing yeast. The final stage is the Distillation Unit, which aims essentially to recover the solvents, to recover bioethanol. Here we have the feed waste dryer. It is an automated system that dries food waste and other organic waste by use of heat and mechanical mixing. So essentially, dehydration aims to reduce the moisture content of food waste, but at the same time aims to homogenize the feedstock and cease any biological degradation of the organic substrate. In this way, as you know, we have an increased moisture content in food waste, which can be more than 75%, and in some cases it goes up to 98%. So by using this dryer, the weight and the volume is reduced by evaporation of the water content, and we produce a dried, manageable end product that has been sterilized and stabilized. Therefore, the dried material does not smell and can be stored for many weeks without any degradation taking place. We have, let's say at this stage, validated the drying system using the sorted biowaste, and the second stage is composed of the bioconversion system. As I said, it is composed of 2 interconnected chambers, having a overall, each one has a volume of 200 liters. It has a rotating shaft for the mixing of the substrate. We did all the necessary works in order to be able to operate for the cases of the WaysTUP project. Then we have the distillation unit, which was designed and constructed in order to recover the produced bioethanol, and the PLC system in order to fully control the operation of the pilot plant. Here I have a short video presenting the operation of a pilot. So after we verified all the different parts of the pilot unit, we performed the first pilot trials using the system. For enzymatic hydrolysis and fermentation, different strategies were applied. in order to explore and optimize the enzymatic hydrolysis and fermentation. We use different conditions in terms of feedstock loading, process applied, enzyme times and dosages. So we've been working with Novozymes in order to provide us with necessary enzymatic formulations, either commercial or not commercial. And by the first results, we obtained the fact that ethanol yield can amounts up to around 58%. So the results show that it's a promising, let's say, approach. And at this stage, we developed the optimization process, and once we achieve that, we will continue with the necessary cycles in order to get the necessary data. Of course, there are technical barriers that need to be resolved, such as the fact that we need to have the necessary feedstock to feed the system. So there are some challenges there. Scaling up, it's not an easy deal, so we have to have a reliable and continuous supply of feedstock. Another issue of concern is the purification of the bioethanol produced to meet the necessary standards. And apart from the technical issues, there are also various barriers in terms of economics, environmental policy, as well as social barriers. Most of these are, let's say, part of the WaysTUP project to deal with. And so some of this could be an issue of discussion at the end of this session. So at this point, I would like to thank you for listening, and the floor is yours now, Martin. Thank you all.
Thank you very much, Dimitris, for the clear and interesting presentation. So I kindly ask the speakers for this section of organic fraction presentation to turn on your camera. So Ines, Caterina, Juan, Dimitris, and Michael. And we are running out of time, but I think we'll have like 10 minutes of discussion because we have a lot of questions. I've seen that you have been already replying some of the questions. So what I'm going to do is to probably select one question for each of you, and so I ask you to provide like a quick response. So for Ines, there was a question from Simon. So I wonder if you work on bacterial nanocellulose production as alternative to paper and plastic wrapping materials from sugar-rich waste.
No, I think that maybe it's for Caterina, because we are not working with waste paper.
Well, in here it was directed to you, but
okay.
But I don't know.
Okay.
Well, I mean, if Caterina is happy to take the question, so yes, the question is about the work on bacterial nanocellulose production as alternative to paper and plastic wrapping materials from sugar-rich waste.
Well, we are working as I commented in the presentation with different kind of cellulosic wastes, including paper and cardboard and cartoon wastes and different wastes that contains cellulosic material. Then yes, we can work on it.
Okay, thank you. I'm just checking some question for Ines, but I think they were already replied by you, Ines. So I don't know. You want to comment on some of the questions that you replied? Probably you can. You want to comment on probably the one of the questions that you already replied.
I think that I replied most of them. Yeah.
Okay. Okay. Thank you. Then there is a question for Juan. Well, many questions actually for Juan. So the question is about waste waste regulations, right? So obviously this is a barrier for insect, for the production of products from insects. So what is your opinion on this, on the current status of the legislation?
Yeah. According to legislation, insects, but it's more specifically those insects which are going to use for animal feeds, they cannot be produced by waste with waste. So that thing is clear and cannot be moved from there. However, there are other farm animals which can be fed with sludge, as far as they are not going to go to the food chain. And in this case, you can be feeding the waste and then using those insects specifically for industrial purposes, or even maybe fertilizers if the quality allows, but it is possible. What is my opinion? I would like to have everything open, obviously, but I think it's a good process to be now checking the quality and checking that nothing will happen, and later on legislation can move to something more open. So to be closed right now probably is better.
Okay, and there is also a question about the pretreatment of the organic fraction.
There's not really
the digestate that you are using in ValueWaste. So just okay.
There is not any specific pretreatment for that. You want to gain some efficiency. Obviously, it is recommended to be reducing the size of the particle just by milling. It's not really. It's very common and cheap process, so it's not so much. Normally, the water content of this waste is about 80%, so we don't need to be adding more water, and we just can mix, smash everything, mix digestate and the organic fraction, and then the larvae are happy with that thing. Actually, we normally don't readjust pH nor readjust water content. We had it in our protocols, but normally we are not doing because it's not necessary. Most of the time, the larvae just produce just fine.
Okay, thank you, Juan. There are more questions for Juan, but probably you can have a look to them. Thank you, Juan. Dimitris, a question from Gemma. Is it needed a pretreatment process before entering the biowaste into the dryer? If so, which kind of pretreatment are you running?
As I said, in our case, it's a pilot unit. We get separated biowaste from a municipality. So the purity of the material is more than 98%. So from my experience, if you have, let's say, sorted biowaste more than 95%, then the pretreatment required is limited. But if you go for a larger scale, either for demo scale or industrial scale, yes, of course, a pretreatment will be required, but also different, let's say, dryers could be applied, not as in our case, the system we use. We can also use a rotary drum or other applications for drying the material. So in this case, a crusher could also be applied for protecting, let's say, the mechanical equipment, and if depending upon the type of source separated scheme that is applied in the municipality and the purity of and the level, let's say, in quality of quantity of impurities, can also be applied different, let's say, systems for extracting and collecting the non-degradable material.
Thank you, Dimitris. There was a question for Caterina, but I think it's general for Excalibur. So it was a question from Simon about the multi-stakeholder. So how do you cope with policy and practices from different scales of waste producers? So what mechanisms in management and finances have you seen to enable these networks?
But it's for me or for
yeah, it's directed to Caterina.
No, I said, okay, can you repeat, please? Because you say it's for Excalibur, and
the multi-stakeholder. So how do you cope with policy and practices from different scales of waste producers? Mm-hmm. I think the question is related to the fact that you are getting waste from different places. So yeah.
No, in our case, for example, in our case, that we are dealing with municipal solid waste and carton and paper, we take this material from the same producer, that is the municipal solid waste treatment plant of the city in which we are working. Okay, but of course, if in the project, for example, that we have different in WaysTUP project, that we have different pilots in different parts of Europe, we deal with the waste that are produced in the city, in which is the pilot installed. But the idea is just to be reproduced, because we have different wastes, for example, coffee wastes, protein wastes, but these wastes are common in the different cities of Europe. Then the idea is just to be able to treat all these wastes in a multi-biorefinery facility. But in our case, for example, we deal with the big producer of municipal solid waste, because if we are in a city, they produce enough waste and enough carton and paper to be treated with our technology. I don't know if I answered the question. If not, please let me.
Okay, I think so. I think now, yeah, we are really running out of time, so I'm going to share my screen for the last words. Okay, so please, well, first of all, thank you very much to all the panelists and to everyone that has been today connected, and for your contributions. Has been a great debate, and obviously the feeling is that we need more time to discuss, because I was trying to read the questions and the answer, but it is obvious that this is a burning topic. That, I mean, technologies. So obviously we rely on technologies for the production of added value products, and obviously this is one of the main challenges for making the urban bioeconomy possible. So please, let's stay in touch. We are building in HUP a network of cities and regions. So you are a representative from cities and regions. So go online to our website, and you can be part of HUP. As I was saying at the beginning, this is one of a number of webinar series on a number of challenges for making, as I was saying before, possible the urban bioeconomy in Europe. So the coming one is also very interesting on new business models, the 10th of June. So make sure that you register and you are present in this very interesting webinar. We also have the one about safety and acceptance of bio-based product, very important. And finally, the last one on policy influence, that is also, as you know, very important. And yeah, so this is what I was saying before. This is a little bit the description of the next webinar, and that's all from my side. So thank you very much, and yes, stay safe, and we'll see each other soon. Bye-bye.
Bye, thank you.
Bye, everybody. Thank you.
Bye, thank you.
Bye-bye. Thank you.
Bye.
Thank you. Bye-bye.
Bye.